Hello, this is the continuation of the Chapter 3 lesson. The first slide is about dimension placement. Dimension where feature contour is shown. This is about where to place dimensions. So in this particular case, we have this feature shown in this view. So we're going to apply the dimension to clearly show where it is. Okay, so for example, this 0.38 is shown in this view instead of this view because I can clearly see where it is. Here we have some poor practices, so take a look at those and compare and contrast. Again, this should be review for you. Okay, then another thing to want to do is dimension between the views. Okay, so in this case, we're looking at the proper practice, the correct side. See, the dimension 2 is between the views. Over here is poor practice. So we're not dimensioning between the views, we're dimensioning outside of the views. It's just poor practice. And then here is another slide on dimension placement. You want to place the dimension outside of the object, not on top of the object. Okay, so what we've done here with the ½ dimension, the 0.5 dimension, we have moved those extension lines out so we're not dimensioning within the view of the object. Same here with the 0.18. Avoid crossing extension and dimension lines. Okay, so what we have here is poor practice. Okay, the 75 dimension is crossing extension lines here. That's sloppy work. Okay, again, this is a review for you. So what you want to do is dimension these things so the extension lines don't cross dimension lines. Stagger the dimensions for readability. Okay, in this case, we have these dimensions here are staggered. Okay, and then once they start lining up on top of each other, you kind of lose clarity. So you want to stagger your dimensions. Avoid dimensioning to hidden lines. Okay, so what we've done here, this is poor practice. We've dimensioned to this hidden line in the slot. What you really want to do is dimension to the view where you can see the slot. And then center of the hole is visible, and that's probably the best place to put the dimension for the location of the hole, is where the hole is visible. So avoid dimensioning to hidden lines, and then dimension holes to the view that you can see it's a hole. Let's talk a little bit about double dimensioning. Double dimensioning is poor practice. Okay, so in this view right here, what we have is we have 4 dimensions. Okay, now if we were to apply tolerances to all of those dimensions, it's wrong. Something's got to give. So really what has to happen is that one of these 4 dimensions needs to be the reference dimension. Okay, so you can't really apply tolerances to everything. So that's double dimensioning. Here's another slide on it that shows the proper practice. Okay, in which case we have not dimensioned E to F. And then E to F is where the tolerances will culminate. So for instance, if we looked at 2.25 minus 0.75 minus 0.75, the nominal from E to F is 0.75. And essentially what we've done is we added up the tolerances, 0.02, 0.02, 0.02, and what we have here is 0.06. So we don't put a dimension on E to F, as manufacturing will allow that dimension to be the culmination of the other dimensions. And again, this is a good place to use a reference dimension. May be applied to features controlled by other dimensions, which is exactly the case here for dimension EF. So we could put a reference dimension on that. Does not indicate any accuracy, it's just a nominal value, and does not cause double dimensioning. So a reference dimension, you put parentheses around the reference dimension, and it does not indicate any accuracy. The other thing we could do is dimension with notes. Specific notes may have a leader, may have a note number and reference list on the drawing, whereas general notes, they apply to the entire drawing. That was like all units in millimeters, okay? Or separate notes and a parts list. Okay, that's where you can have cover sheet containing names, approvals, and model numbers. You can have a note sheet that might be required. Okay, I want to talk about fits for a little bit here. We have three basic kind of fits. Okay, so two parts that fit together are going to have tolerances. Each one of those parts is going to have tolerances. So a clearance fit says regardless of the tolerance condition, as long as the parts meet their respective drawing tolerances, when you put these two parts together, the internal part will always be smaller. It's a clearance fit. No matter how it goes together, it fits together. An interference fit, by the contrast, is where you have a tolerance condition where the internal part can be larger than the external part. An interference fit will always be larger. The internal part will always be larger. Whereas a transition fit, it may be a clearance or an interference fit depending on what the tolerance condition is of each of the parts. A line fit is a limit condition where internal and external parts are the same. Zero allowance. We'll talk about allowance in a bit. Here's an example of a clearance fit. Okay, so with the smallest hole and the largest shaft, we'll always have 3/1000 clearance. That is a clearance fit. Okay, so the minimum clearance is known as the allowance. So in this case, the allowance is 3/10. I read 0.0003 as 3/10. Here's a transition fit. Okay, if we take the smallest hole minus the largest shaft, what we end up with is -8. That's an interference. 8/10. That's an interference fit. But if we take the largest hole minus the smallest shaft, we end up with a clearance of 9/10. 9/10 of 1/1000. Okay, so that is a transition fit. Here's a line fit. If we take the smallest hole and the largest shaft, our allowance is 0. That's the special case of a line fit. Okay, and then on the clearance side, if we take the largest hole and the smallest shaft, we have 1.5 thousandths of an inch clearance. Okay, in geometrics, we're going to use feature control frames. This is an example of a feature control frame. We'll be talking more and more about this, but I just want to introduce this here. Feature control frame always contains a tolerance symbol. Okay, here is the tolerance symbol. It's the geometric characteristic that the feature control frame is trying to control, and it always contains a tolerance value. In this case, the 11/1000 here is the tolerance value. There's other components in this one. Here's the shape of the tolerance zone, and these are datums over here, and this is an MMC modifier, but we're going to be talking about all of that in future chapters. And this one introduces you to what the modifiers are. So a circle with an M in it stands for maximum material condition if it's used in a tolerance, and it stands for maximum material boundary if it's used in a datum reference. And L is the least material condition. And again, we're just introducing this here. We'll be talking about this extensively in this course. Okay, stopping.